Today, let's dive into a truly captivating realm where physics meets the human brain. Imagine just for a moment that we're not just exploring a part of human anatomy, but embarking on a journey through a universe within our heads. Ready? Let's get started. First off, consider the brain as an intricate energy system. Picture this. Every thought, every memory, every blink of an eye is powered by neurons firing electrical impulses across tiny gaps called synapses. It's not unlike electricity flowing through a city's vast network of circuits. But here's the twist. Every spark of energy is meticulously conserved, transformed from the food we eat into a form cells can use, much like a city converting resources into power it needs to thrive. Now let's delve a bit deeper into the possibly stranger side of physics, quantum mechanics. Yes, you heard right. Some scientists propose that the enigmatic laws of quantum mechanics might influence our thoughts. Imagine neurons operating not just as simple on-off switches, but as complex quantum devices, processing multiple possibilities at once. It's a speculative leap, and admittedly, our brain's warm and watery environment isn't exactly friendly to quantum phenomena. But what if? Moving on to something a bit more relatable, relativity. Einstein's famous theory might seem worlds away from our daily experiences, but it does make you wonder. The brain governs our perception of time through its internal clocks. High-stress situations seem to slow time down, don't they? While this isn't relativity in the scientific sense, the metaphorical parallels are fascinating. Could our mind's eye be a playground for relativistic effects? It's food for thought. Lastly, picture the brain as a cosmos. With its 86 billion neurons and countless connections, doesn't it remind you of a star-studded sky? Just as gravity orders the cosmos, electrochemical forces mold the neural pathways, crafting the unique landscape of each mind. In this light, each brain is not just an organ, but a universe unto itself, vast and ripe with mystery. So there we have it, a voyage through the brain seen through the lens of physics, from energy systems to quantum mechanics, from relativity to cosmic analogies. Isn't it thrilling to think about our brain as more than just biology, but as a frontier of physics? Now that we've journeyed through the brain from a physics perspective, let's dive into another intriguing concept, entropy, and how it relates to memory and forgetting. Entropy, a fundamental principle in physics, is often associated with disorder or randomness. When applied to the brain, it offers a unique lens through which we can understand how memories are stored, maintained, and eventually lost. Consider entropy as a measure of uncertainty in our memory system. A low-entropy state implies that the system is highly ordered, where information is well preserved and easily retrievable. In contrast, a high-entropy state suggests a system where information has become disordered, making it difficult to access specific memories. The brain works tirelessly to maintain a low-entropy state within its neural networks to preserve information. It does this through mechanisms like synaptic strengthening and creating redundant pathways, which help stabilize memory traces against the natural tendency toward disorder. But what about forgetting? Think of it as an increase in entropy within the neural networks responsible for memory. Over time, without reinforcement, the synaptic connections that form a memory can weaken, akin to the decay of a signal. This decay leads to an increase in entropy, making the original memory less distinct and harder to retrieve. Recent research has explored advanced forgetting models in neuromorphic memory systems inspired by biological neuronal systems. These models incorporate factors that modulate the rate of decay or forgetting, effectively managing the entropy of the system. From a thermodynamic perspective, memory can be related to physical traces. Consider footprints in the sand or craters on the moon. These are macroscopic phenomena related to an entropy gradient, ultimately stemming from past low entropy. The second law of thermodynamics, which states that the total entropy of an isolated system can never decrease over time, implies that traces must be related to an entropy gradient resulting from past low entropy. The maximum amount of information stored in memory can be quantified as a function of relevant thermodynamical parameters. This transformation of low entropy into available information suggests that all macroscopic information may originate from past low entropy. To have memory, there must be an initial difference in temperature or energy, a past low entropy condition, because maximal entropy requires equilibrium. So as we ponder the relationship between entropy and memory, we uncover a dance of order and chaos within the brain. As we continue our journey through the fascinating intersection of physics and neuroscience, let's delve deeper into an area that's pushing the boundaries of technology and understanding neuromorphic memory models. Neuromorphic memory models are an advanced area of research that draws inspiration from the structure and function of the human brain to design computing systems. These models aim to replicate the brain's ability to process information efficiently and adaptively. Let's delve into some key aspects of neuromorphic memory models. Neuromorphic engineering translates our knowledge of the brain's function into computer systems, focusing on replicating the analog nature of biological computation and the role of neurons in cognition. The biological processes of neurons and their synapses are complex, involving analog chemical signals which are challenging to simulate artificially. However, the characteristics of these processes can be abstracted into mathematical functions that closely capture the essence of neuron operations. Neuromorphic computing systems can be either digital or analog, with the part of synapses played by either software or memory stores. Memory stores, in particular, are useful in modeling synapses' ability to store information as well as transmit it, providing a more brain-like functionality. A significant feature of neuromorphic computing is the use of spiking neural networks, SNNs. Unlike traditional computing based on transistors that are either on or off, SNNs can convey information in both temporal and spatial ways, similar to how the brain operates, thus producing more than one of two outputs. This allows for a more nuanced and dynamic form of computation that can potentially lead to more powerful and efficient computing systems. Neuromorphic networks are a hardware implementation of artificial neural networks. They resemble cooperative phenomena and can process probabilistic, noisy, or inconsistent information. The familiar examples of these models include the Hopfield network and its improved successor known as the Boltzmann machine. The implementation of neuromorphic computing on the hardware level can be realized by oxide-based memory stores, spintronic memories, threshold switches, and transistors. Neuromorphic memory models promise significant advancements in computing, offering advantages such as reduced energy consumption, increased processing speed, and the ability to handle complex adaptive tasks. As the field progresses, we may see neuromorphic systems becoming more prevalent, potentially transforming the technology industry and leading to the development of more intelligent and autonomous machines. In essence, neuromorphic memory models represent a convergence of neuroscience, physics, mathematics, computer science, and electronic engineering to create systems that not only compute, but also learn and adapt in ways that are reminiscent of the human brain. The future of computing is bright, and as we continue to explore these cutting-edge technologies, we edge closer to unlocking the full potential of human-like artificial intelligence.